This is part 1 of a gentle introduction to Merkle trees. In this part, we're going to learn what binary Merkle trees are, what Merkle roots are, and what proofs of inclusion are, or Merkle proofs. So first, what is a Merkle tree? So simply put, a Merkle tree is a way that we can take a large amount of data and compress it down into a single value while still being able to efficiently prove facts about the underlying data. Merkle trees are used all over the place in blockchains to commit to transactions in state, allowing light clients to verify activity without downloading the whole chain state. They also underpin transparency systems, package managers, version control systems, and other distributed systems where we want to enable efficient, tamper-evident verification of data that's served by untrusted parties. Here's a picture of a binary tree. So binary here just means that each parent node has two children. So what makes this a Merkle tree? So let's say we have 4 data chunks, D0, D1, D2, D3, and I want to construct a Merkle tree out of this. So what I'm going to do is at the very bottom of the tree in the leaves, we're going to store the hashes of our data. So from left to right, each leaf is a hash of one of the data chunks. So the leftmost node is the hash of D0 to the rightmost node, which is the hash of D3. Above them, every internal node is just the hash of its children. So for a binary Merkle tree, we have 2 children, as we stated. So we're just going to concatenate the 2 child hashes and hash those. And that's going to be the value of each internal node. And we're going to proceed doing the same all the way up until we get to just one node, and that is our Merkle root node. And we constructed this in exactly the same way by hashing the 2 children. So if you look at protocols that involve Merkle trees, the roots are very important. So what is the significance of this Merkle root? So it has some properties that are particularly useful. So the first is that the Merkle root is a succinct commitment to the data. So what does that mean? Let's go back to our picture. So if I change any bit of any of these leaves, so let's say I modify D3 to D3 prime, then the value of that leaf node is going to change because this is a hash function. So instead of having L3, I'm going to have L3 prime. Similarly, its parent is going to change because I'm now hashing L3 prime to get P1 prime, as will ultimately the root. So if all we get access to is the root node, I don't even need the whole tree or the whole data set to detect tampering. If the root hash changes unexpectedly, then I know that the data has been tampered with. And it's also a very small value, which is 1 hash output. So that's the first very handy property. The second nice property is that we can do efficient verification of membership of data items in the tree, i.e. inclusion. So let's say that I want to prove that item D3 is included in the tree. So I don't need to send you the entire tree to prove that to you. I can send you the data item I want to prove, D3, or its hash, L3. I can also send you the sibling hashes along the path up to the root node. So here I'm going to send L2, which is the sibling of L3. And I don't need to send P1 because the verifier can compute that from the 2 values L2 and L3, which is it has or is able to compute. And then I also need to send P0, which is the sibling of P1. So with that, the verifier can hash together this Merkle path or Merkle authentication path. So they'll hash L2 and L3 together to get what they think P1 is. They'll hash the provided P0 together with what they thought P1 was to get the root value. And then they'll check that the root matches their trusted root that they have in their data store locally. So provided the hash function is collision resistant, it's computationally infeasible to produce a different piece of data and authentication path that results in the same Merkle root. So One of the reasons that is so powerful is so in a binary Merkle tree, every time you move up one level, the number of nodes is cut in half, as we can see from this picture. So in a tree that has n leaves, it's going to have a height of log 2n. So to prove that one leaf is included, you only need the sibling hash at each level along the path to the root. So that's one hash per level for a total of log 2n hashes. So it's worth noting that you can have other branching factors. So we've shown a binary Merkle tree, but you can have a quad tree, so where there are 4 children per parent. And in the arbitrary case, a node is going to have k children, and so the height will then become log kn instead of log 2n. So at each level, you'll still need to provide the sibling nodes, but it'll just be the k minus 1 sibling nodes. So increasing the branching factor will change the constants, but you'll still have a proof size that's logarithmic in the number of nodes. So today we learned what a binary Merkle tree is, what a Merkle root is, what a Merkle proof of inclusion is, and how we generate and verify it. Next time, we're going to discuss prefix trees or tries. I hope this was useful, and thank you for watching.